Hello.
Yeah, today we are going to discuss about the assignment number 9 in the course dealing with materials data, technologies, and interpretations. So, I'm Sadar Gagan, and I'm pursuing the PhD in IIT Madras. I'm working in the field of field information behavior. So, most of the time I will be dealing with lots of data. I would say we get through several tests and have to take a lot of decisions from the data which I'm getting. So basically, if you are an academic or civil or whatever engineering, the one when you want to do an analysis, you will be searching for a lot of tools for taking a decision based on the data you have. So that time, this whatever things we are discussing in this process will be very useful. Um, so we'll be discussing one by one. Today will be briefly talking about ANOVA and the problems associated with the ANOVA test. So we'll be saying we will be only dealing with simple problems, but later I'm planning to post a separate video discussing my data, how I am processing on the real time. So let's directly go to the questions. So the first question is the they are given the rate of chemical reactions or rate constant is a function of temperature. The temperature dependence of the rate constant is given by Arrhenius equation. So Arrhenius equation always discusses the rate of occurrence. Like for example, here it can be the diffusion. So where the diffusion rate will be given by the diffusion coefficient. So basically, we'll be estimating some kinetics of an occurrence. So here, this is the Arrhenius equation. K is equal to A into exponential of minus E A divided by E suffix A divided by RT. Here, K is the rate constant and A is Arrhenius constant. E suffix A is the activation energy for the reaction. Can be whatever reaction, chemical reaction or thermodynamic reaction. So depends. This is like universal. We can use it wherever we want. Then R is the universal gas constant. Um, and it is the temperature in absolute scale, which is Kelvin. So whenever we discuss or whenever we solve the problems, are like, one second. Whenever we solve the problem related to this rate, yeah, rate of these occurrences, like it is better to use the absolute scale, especially in this case, we should use the absolute scale of Kelvin. So, can this equation be written in linear form? So, to write this equation in linear form, we have to take log on both the sides. So, can we take log on both sides? Sorry, log of k is equal to log a plus, since it is an exponential, it will be like log of exponential of minus E by RT. So can simplify it as log k is equal to log A plus or like minus B suffix A by R. So this is the same equation in linear form. Here the slope is given by minus E by R. So it is like y is equal to mx plus, again, sorry for my handwriting. Is y is equal to mx plus c. Here y is log of k is equal to ms minus EA by R into T max plus log A. So this is the additive slope here. So this we will be dealing in the further next problem. We'll know the significance of it. So this is the linear form. Again, I have written it in the digital. Okay. Next, what they are asking is like the following reaction of NO2 decomposition obeys the Arrhenius equation. It's a chemical reaction which is obeying the Arrhenius equation, and the reaction rate as a function of temperature is given in the file. In the file, they have given the x and y value like react temperature and the energy. So they're asking us to fit the ln k versus ln k in the y-axis and the temperature on the x-axis as a linear fit. The slope and intercept of the fit, or they're asking the slope and intercept of the fit. So basically, as I discussed on the last one, uh, the slope is negative minus EA by R. Then the x is 1 by t, y is ln k. It's a semi-logarithmic plot. So okay, so they are asking the intercept slope and the intercept values. So first, how we can this can be solved in pen and paper also, but I prefer to do it in the program or language. So first, what I did is like yeah, I just invoke this. I saved that file as NRR. It's like NO2 reaction rate. This one I saved it as NRR dot CSV. Then what I did is like I just read this CSV file to the variable called VAL, and then I just invoked that first column value temperature in Kelvin to X. Then using that dollar symbol, then using the again I invoke this Kelvin K in per mole per second to the Y. So next what I did is like as I know the x-axis is in x-axis is 1 by t. I just made this small arithmetic small calculation where I changed the values of x to 1 by x and stored it in on t. So the now temperature value is stored in T in Kelvin inverse, sorry. Then again, the next one, whatever are the values which I stored in Y, I have taken it to K. And K is K to the log of Y. So now, this if we just put a log Y means it will be like uh, to the natural logarithm. So, 1 second. Hello. I'm audible. Sorry for the interruption. Okay, I had some issue with the mic. So yeah, here what we are discussing. I have invoked the values in log. So if I want the values to be in the, if I don't specify any log base like log 10 of y means it will come in the log based log 2 of y means to come in log based. If I don't specify any specific value, then it is just the then it is just the it is clear that it is without any base, which means like it's natural of the time. So yeah, now I just plotted template one by t in the x-axis and k in the y-axis. This is log plot. This is linear plot. So when you plot this, we got the points here for the five values, whatever we gave input. Then what we did is like gave the uh, linear regression model of k with respect to t. So we are trying to find a relationship, like linear relationship between K and T, and then we are making that line, drawing the line, which is red in color, AV line of fit color is equal to red. So in that way, it will draw a line. So now what we want to know is like we want to know the intercept and the slope value. So for that, we just um, yeah. So we just get the we just give the coefficients. Coefficients will return the coefficients of the particular function. Here the fit has two coefficients. One is shift and sorry, one is intercept and another one is slope. So these are the coefficients. Like each and every function or variable has different um, coefficients. So their coefficients will be returned as returned when we give either CO here, this one, or if you type completely as coefficients also, it is fine. So print coefficients of fit and you will get the intercept and the slope value. So let's go back and see. You have the slope value of minus 13571 on intercept value of 39. So A is the right answer. So here, whatever you have got is only slope. If they ask you to find out the, if they ask you to find out the activation energy value, means what you have done is like uh, minus CA by R is equal to minus 13,571.76. Now E just cancel the minus minus. Then EA is equal to 1357 into R. So when you substitute the R value according to the units, whatever the 1357 value is in, then you will directly get the value in their respective units. So this is how you have to find the activation energy value. Yes. So moving on to the next question. So yeah, okay, I forgot this. So the next question is actually the activation energy calculation. As I told, you have got the slope and intercept. So you can directly let's see, substitute in this minus EA by RT. In that minus EA by R is the slope. And we have got the R value is 8.314 joule per mole Kelvin. So now we can easily get the activation energy value in terms of kilojoule per mole. So answer is C. So before moving on to the fourth question, I just want to introduce the concept of ANOVA. So ANOVA is what? ANOVA test is a statistical test used to analyze differences among the group. You know, a group uh, from that we would have taken a sample. We will analyze the sample and we will find we will analyze the differences whether there is any difference or not. So it's from this result you will just clear that they are used for this can also be used for hypothesis testing because what is hypothesis testing? We will propose a null hypothesis, like we will see whether there is any uh, difference in the behavior or not. If there is a difference in if we will propose like there is no difference in the behavior as null hypothesis, and there is a difference as alternate hypothesis, and we will try to uh, prove that our null hypothesis is uh, yeah, we will try to prove our null hypothesis. So that is H naught. So why we are suggesting null hypothesis like no differences because the region which has no effect is very small, like 0.05%. It's less than, yeah, it's like 5% only. So this is very easy to tackle. But the region which has, if it is two times less, the region which has alternative hypothesis or like there is a difference has a large region. So it is always easy to attack the small region and we can find out whether the value is exceeding or not. If it is false within the critical value, um, then the null hypothesis is valid. If it is like more than that, or like if it is exceeding that, okay, let me make it clear. The for Z test and T test, we calculate the p value. If the p value is within the significance level, then like significance level is 0.05 means if the value is less than 0.05, then our null hypothesis is valid. Or sorry, the null hypothesis the null hypothesis can be the null hypothesis failed to get rejected if the value is more than the significance level, the null hypothesis will be rejected. Which means intuitively the alternative hypothesis is valid. So for the hypothesis testing, we can use the ANOVA test. So now what we are going to do is like we will first learn the basics how the ANOVA test we can do it in pen and paper. Then we will go for the R language and we will correlate the R language with our pen and paper based calculation. So as I told in ANOVA, we use F statistic to test whether the group means are equal or not. It can also be termed as a ratio of variance between the groups to the variance within the group. So between the group means if say if I take three groups, you can see here, right? Blue, um yellow, and green. These are the three groups, and if they have some variance between them. Variance is like from the mean how much they are varying. Then for variance, yeah, this is variance between the group. You can see in the A, and this variance is very less between the group. But if you consider the B category, like they have a huge difference in the variance between the groups. So, but if you see here, the variance within the group is small compared to the variance between the groups. And variance, actually, but if you see here, right, the variance between the group is high compared to variance between the groups. So what I meant to say is like if, this indirectly tells that um, there is not much variation between the three groups because if you see that within a group itself we have so much variation. when we are comparing between the groups, the variation is very less from kind of for the between the group compared to within the group. So there is no variation or there is no major change in the change between the groups. Or otherwise, we can put it like null hypothesis is valid, which means there is no difference. But in the right side case, the variance between the group is high, which means like there is an effect. Yeah, the right term is there is an effect because of the uh, performance of the three different groups. Whereas the variance between the group is small. Uh, With this insight, let's go deeper into this topic. So there are two types of generally classified under two types of ANOVA test: one-way ANOVA test and two-way ANOVA test. One-way ANOVA test is used when you have one independent variable. Like one independent variable means we can say can take an example here of what I have given. Investigating the effect of heat treatment methods on hardness of an alloy steel. Um, like if we have three different heat treatment conditions, like normalizing, quenching, and tempering, how they are influencing the mechanical properties such as hardness. Or like if I am doing three different heat treatment, how it is influencing the tensile strength or ductility, all those things um, comes under the one independent variable thing, which is one-way ANOVA test. The two-way ANOVA test is this involves two independent variables that is used to determine whether there is an interaction between these variables on dependent variables or not. Like how these two variables have are influencing the dependent variable, and do they have any interaction between these variables? So best example is like in terms of our testing, mechanical testing, we can see this impact toughness. Toughness of different steels depends on two things. Like if you take steel, if you're varying two things like the carbon content and heat treatment. So based on the heat treatment, the martensite fraction will vary, and also based on carbon, the martensite fraction again will vary. So both has an interrelationship, and both can influence the mechanical property, which is the toughness. So here there are two independent variables which is influencing the dependent variable, which is toughness. So for this kind of test, we can use two-way ANOVA test. Yes. So these are the types of ANOVA tests which we can perform. But in this session, we are limiting ourselves to the one-way ANOVA test. So how to perform that? First is we have to record the data for the and categorize them. Sometimes we'll have the data in terms of category itself. So then we have to find this is the table which I generally use like variation source means as I told, right? So between what is the variation between the groups and what is the variation within the group. So this is what we are basically going to find. There is nothing difficult in this. So a variation between the groups. There will be a uh, question from you, like why we are calculating the variance, why not other things? Because even if you consider only the mean, right, every value can come close to the mean. But if they have so much variation in their collection of data itself, then it will easily fool us. The data, whatever interpretation we are taking with, might not be correct. For example, if I measure three group of people or three set of samples, one has 190 MPa strength, mean strength, and another one has 250 MPa mean strength, another one has 220 MPa mean strength. This is average strength. This is what I'm discussing. But if during my test I'm getting a difference of I'm getting a difference of plus or minus some 60 MP. So here I'm getting plus or minus 5 MP. Then I'm getting plus or minus 30 MP. Then if you see the highest it can go is like around 250 MP, and lowest it can go is like 245 MP. And the maximum it can reach is again 250 MP. Hence we cannot tell we cannot tell clearly like which one will have we can tell which one will have essence only with respect to mean, but only when we see their standard deviation or variance, then only we can be like 100% sure. So the variance plays a major role in determining the uh, output of the analysis because they import a huge difference. So that's why we are analyzing the variance. And also, during this process, we use this mean square. Mean square means it is like some of the difference in some of the squares of the difference in the value from the mean. So that is what we are going to calculate. So why we are calculating the sum of the difference in the squares or degree of freedom difference then minus probability. So why we are doing this is yeah, this is the mean square sum of the. So you can see this closely resembles the variance. So this one is closely resembling the variance. So that's why which means like we can put it in the other way. Mean square is the estimate of variance. So that's why this here we are indirectly estimating the variance in terms of mean square. So okay, this is the basic which is made now clear. Mean square means this is what we are calculating. So now we will be telling whether the hypothesis is valid or not based on the F value. If F value, okay, for calculating the F value, let's go one by one. So between the treatment, the variation between the treatment is called, or the mean square, which we calculate for the difference in between the treatment. Okay, let me go on by one. So when it is between the treatment, the formula for the sum of the squares is um, summation of xi bar minus gm the whole square. Here, gm is nothing but the grand mean. Grand mean means the mean of they have taken four set of samples. Each sample has an average of say mu one or two. Uh, so grand mean means GM means if the mu one plus mu two plus mu three mu four y four is it and or mu I plus to n divided by n is given as grand mean. So these are all the xi bars. Mu one, mu two, mu three, mu four are the xi bars. Then this is how we find sum of the squares between the treatment. Then degree of freedom between the treatments. So degree of freedom can be the degree of freedom between the treatments can be given by number of experiments or number of groups we have taken minus 1. So we need the number of experiments minus 1. Okay. Moving ahead, the mean square is given by uh, sum of squares divided by area of the length. Or we generally call it as, we can use this term, uh, mean square difference the treatment MST divided by D dt dft or dt. Got it. So next, error within the treatment. So for this, what we have to do is like, see, let me make it even more clear with an example. If I am taking four groups, let's say A, B, C, D, one, two, three, six. So this will have one mean value. This will have mean value. This, you have four different mean values for A, B, C, D. Now, with this, and for between this mu1, within this mu1, mu2, mu3, mu4, if you add and divide by 4, you will get the grand mean. So with that, you can find out the, and you have four experiments or four groups. So degree of freedom is 4 minus 1, which is 3. And now if you see within the treatment, right, or error, we call it as error, means error in the measurement or error in the variation. For that, it is within the treatment, which means like within this group itself, we have to find the uh, sum of the squares. Which means like what you have to do is the summation of, I think, state. One second. Okay, sum of the squares between the treatment is given by n into summation of n into say power minus 3n whole square. Okay, n is the number of sample size between the treatment. I think we are using different terms. Should be somewhat clear. So what we can do here is, yeah, we can use levels. This we have this four treatments, right? Or four groups, right? Which we can call it as A. So we'll keep it here as A. So there won't be any confusion. So degree of freedom is A minus 1. A is a number of levels or number of groups or number of experiments, whatever we are taking. It's like number of, we can follow this number of columns. It will become very easy. Then this, within the column, we have several test samples, so that can be taken as rows. So yeah, now it is very clear. Now we can go ahead. So, so, to find the mean square of this error or within the treatment, First, we have to find the sum of the squares. Sum of the squares, how we can find this is simply let's say now it's 5 bar the whole square. Just simple variance. Then what you have to do is like you have to find out the degree of freedom for the error. So degree of freedom for the error is given by a into n minus 1. So we know here A is the number of groups or columns, n is the number of rows, number of samples we have taken in each group. So yeah, here number of samples we have taken is 1, 2, 3, 4, 5. So 4 into 5 minus 1, 4, 4, 16. 16 is the degree of freedom for the error. So now we have to do sum of the squares. Sum of the squares means just divide the first and second and third column. So what you will get people call as MSC, mean square error, divided by DE, degree of freedom associated with the error. So now we have got a mean square for the, we got MST. Mm, sorry. Okay. We can call this as T. We can call this as E. So MST means mean square of difference between the treatment of SS SST divided by T by dt or whatever you can call it. And then here MSC is given by SSE divided by D or dy. It skips over similar terms. So now we have found MST and MSC. So just we have to divide the MST by MSC, that is the value. So to make it more clear, MST is given by SST, sum of the squares of the difference between the treatments divided by dt, degree of freedom of the difference. This can again given by summation of n into xi bar minus random the whole square divided by a minus 1. A is the number of levels or experiments or whatever. This will be the column. This is MST. Then C mean square of error is given by S plus C divided by D suffix C. Then this can again be written as summation of xi minus xi bar the whole square divided by a into n minus 1. So this is the basic form. Then we can take f value is given by n minus t by n minus c. Okay, so n minus t by n minus c. So this can be given by uh, Mr. Bemasi, this can be given by okay, sorry. Basically, we will get a value for this. If it is large, then then it denotes that there is a difference. As we discussed, right? If the difference between the treatment is larger compared to the mean difference between within the treatment, then there is an impact or then there is an effect, as we have discussed in the slide. So you can, in this case, MST is approximately equal to MSC. So there is no difference, no effect, no effect. Here MST, sorry, must is for greater than must. That's why you find the difference. So unless we see an example, we cannot appreciate this. So let's look at an example. So for example, we can take the fourth question. The fourth question, just a minute. Yeah, for the interruption. Yeah. Let's take fourth question as an example. In this question, consider the measurements made by four different laboratories, A, B, C, and D, as like we have discussed before, and four samples of each lab or has been tested, and the results of the measurements are shown in the table. Carry out the ANOVA test, ANOVA, one-way ANOVA for the given table, which means that it is dependent variable. We have only one dependent variable. Which one of the following options will indicate the results of the ANOVA test? So let's try to solve it in pen and paper based method. So don't worry, like I already used Excel to solve this. Otherwise, it will become difficult to explain everything here. So let me explain. So this is the given data. This is the given data. Lab A, Lab B, Lab C, and Lab D, and I just find the mean value for each one. So that is X. Second. U A, U B, U C, U D. Okay. These are the mean values for each thing. Then, as you have seen in that table, have find the mean sum of the squares uh, for each condition. What I did is like I made the sum of the squares. Okay, so this is sum of the squares. Treatment just C. So in the sum of, yeah, I hope I'm audible. So sum of the squares, sum of the squares is nothing but difference from the mean, square of the difference from the mean, and then summing it up. So maybe sum of the square is then for SST, what we have to do is that we just in any yeah, A into sum of the squares. So that's how we have got, this is the MST. Okay. So similarly, within the treatment, okay, before that, how we calculate the sum of the difference between the treatment is, I have calculated the grand mean. This is grand mean. So from the grand mean, I have taken the difference, like 76.5 minus 70.43, the whole square. So that we have to give 36.75. Then 70 minus 70 minus 70.43, it gives 0.19. Since it is square of the difference, it will only turn out to be the positive value. Then similarly 67, because the difference is close to 8, then 6.5. Then I have summed up all these things and multiplied by 4. So 110 something it came, and 110 into 4, 442 we got. That is MST. Similarly, for MSC, what I did is like, what we have to do is, so I have the mean value. Generally for variance, how we do, subtracting from the xi minus mu x bar a, the whole square. Then xi is now 78 minus 76.5 the whole square, like that I did. Then summed up. Then finally we have to sum all. Here how we did the sum, and we have got this into with multiplication. Here also we have to do the sum to get this value. This is MS. I mean, sorry, this is the sum of the squares between the treatment and sum of the squares between the error. So once we divide it by degree of freedom only, you will get the MST and MSC. So which is the mean squares. So here degree of freedom is 3. So we just divide this SST by 3, that is 442.88 by 3. So we get 147 as the MST, and then similarly we divide 125.75 by 12. We get 10.47 as MSC. So now if we know F value is equal to MST by MSC, so we get 14.06 also. So this is how we generally solve it in pen and paper method or using Excel. Uh, this is very simple if we solve it using R. Let's see how to solve using R. Okay. So for that, I'm invoking these values from 75 to 80. Starting from 75 to 80, I'm invoking these values to a variable x. And what I'm doing is that then I'm segregating these values to labs. Lab is equal to factor of factor will categorize the values with respect to repetitions of C of A, B, C, D. Each time for 4 values, it will take it as A, B, C, D. For example, 75, 73, 60, and 70, right? Once it will assign 75 to A, 75 to A, 73 to B, and 60 to C, and 70 to D. Again, it will, since we have given 4, again it will go back to A. So next value is 78 will be stored to A, 71 to B, 64 to C. So like this, it will store. You can also store it in terms of matrix given. That's also possible. This is one way of invoking the values. So once you have given, you are you're defining a variable called model, which is equal to you are comparing you are taking the linear regression model between x and lab, x with respect to lab, I can say. we can say. So X is here. Um, yeah, yeah. X is here the table of values, and we are relating it with respect to lab. So what we are trying to achieve now is we are just checking the ANOVA of model. So it will try to get a linear relationship between the category and the given values. So now it will check ANOVA of model. We get a result like this. So in this we get the F value. We get mean square value, like whatever we have calculated, we will get it directly. So residuals also we will get. Residuals means errors. Errors whatever we have calculated right within the treatment. So that also we will get. So from this we can know what is the f value. Since f value is very high, like 14 times higher than the um, 14 times higher compared to the it should be like close to 1 or 0, like the value should be very less, but it is 14 times high, which means the value is very large and there will be an effect. So what the questions they are asking is, I think they are asking for the results only, right? Then this is the thing. Yeah. Let's compare it and answer. So moving on to the fifth question. Fifth question is a research scholar in MEMS department at IIT Bombay performed heat treatments on identical steel specimens in three different furnaces. Then she carried out a mechanical test on these samples to found significant differences in properties. Given this scenario, she wants to test the null hypothesis, namely that all three furnaces are actually at same temperature. So she has made 5 readings of the temperature from each furnaces and data is collected as given below. So basically what she has did is like this is a typical problem where even if we don't calibrate each furnace in our lab, then they can the temperature in the three furnaces can also be different. Hence we should use a common thermocouple to check all the three temperatures of the furnace before carrying out any experiment. Otherwise, it is better to carry out all your experiment in one single furnace, provided that you are keeping the maintenance regularly on. So here in this typical problem, she has three furnaces. There is one, two, three, and each furnace she has kept 5 samples for the testing. Like in each furnace, she observed five temperatures, and she wanted to compare whether there is any um, variation or not. So null hypothesis is like there is no difference, which means that it is perfect. Which means that all are at same temperature, like close to 600. So that is a null hypothesis. The alternative hypothesis is there is a difference. That is an alternative hypothesis. So now we have to perform the one-way ANOVA test, and using the p-value we can decide. Earlier I told that f-value also we can decide. Now in this case we will decide based on the p-value. So similar to the last problem, we are like invoking the values of the array to a variable called temp. So temp has all the temperature their values. So we are giving it in an array. Then we are categorizing them in terms of here we can use FUR also in terms of plan. Just use the previous program it's deployed. Yes, FUR is equal to furnace is equal to factor of repetitive ABC, and now we will give 5 terms. So 592 to 594 it will be assigning to uh, sorry, 1 second. Yeah. So what it will be doing is 594, 388, then 602. Like that I have given, which means like it should be repeating at three times. So, like written the coordinates three times. Just type through this. So that this like should be repeating three times. Then 592.4 will be assigned to 1. Then 588.4 will be assigned to 2. And 602 will be assigned to 3. Again, 593 should be assigned to 1. Like that it should happen. So model, a linear regression model of temperature with respect to lab. Then we give ANOVA of model. Then it has given the output of p-value. P-value is like, okay, they have given the significance level. Significance level is 5%. 5% is 0.0. So p-value, it is p-value is equal to, sorry, p-value 0. Sorry. P-value is 0.05. Whatever value we have got is uh, less than 0.0, which means like the null hypothesis is failed. Which is like there is no variation in the properties or variation in the temperature is the null hypothesis that is invalid because the value is less than the significance level. Um, Hence it will fall under the failure region. So null hypothesis is failed. Null hypothesis is failed to be accepted. So in other words, we can tell alternative hypothesis is valid. So alternative hypothesis is valid in this case, not the null hypothesis. See, if we have got the value of t, like here we have got right 0.002577. If you would have got it like 0.06 or 0.055, right? Then we would have said like null hypothesis is valid. But here it is very less, so null hypothesis is not valid. So if the value which we have got is greater than the significance level, then it is it is meaningless. Like we have discussed in the last session or last assignment briefly about sorry in detail about this. Like how when we are rejecting the null hypothesis and when we are accepting the null hypothesis. Again, I will brush it again. That topic. If the p-value is less than the significance level, then we can reject the null hypothesis. If the p-value is greater than the significance level, here it is 0.05, then we fail to reject null hypothesis, which means that we are accepting the alternate hypothesis. So that is an so here alternative hypothesis is the answer for the question. Okay. So F statistic value obtained from the ANOVA analysis in the question size. So the statistic value is here we have got is 10.204. So here we have the same answer in the option. Let's happily click this. Move on to the next question. Okay, sorry, here itself I have got the same. And also we can say here the F value is very large, like about 10 times higher than the mean square of error. Hence, the from this also we can conclude like there is an effect or null hypothesis is valid. Next question is state whether true or false. The function QQ norm can be used to check if the distribution is normal. So QQ norm, what it does is like it generates a sample. It generates a sample, normal sample, which follows a normal distribution, and it compares your given set of value with uh, normal generated values. And what it will do is that it will try to fit it normal generated values to a line, sorry, the normal generated value, uh, and sorry, yeah, it will try to match the normal generated values and your value, and see whether it is if it is falling in that diagonal line means it follows normal distribution. If it doesn't follow, if it has a scatter means like it is if the points means, then it is less likely to follow the uh, normal distribution. This is how we can perform a test to identify whether the distribution, whether your data set is following normal distribution or not. Okay, so like I have tried to write a program for this, code for this, to generate a set of 100 random variables. So it provided a seed of 1, 2, 3. See, repeatedly I'm using this because it will generate the identical random numbers, so that when I am comparing it again, I won't be generating a different random number. For example, if you follow this, you will get a similar result whatever I'm getting. Otherwise, if you just give QQ norm this without setting the seed, if you give R norm this, it will generate some completely random, like without any similarity between our what I generated and what you generated. So you'll be getting some 100 normal other random values. But if you give a set seed and if you keep on following that, you will be using the similar random variables for your analysis or test analysis. Yeah. So here X, I'm feeding the 100 random normal variables to X, and then QQ norm X. It will generate um, yeah, it will generate it will plot it with respect to sample of quantiles, here two quantiles, and like as you can see, the scattered points are in the diagonal. Then I am just giving T2 line, and then it will draw the normal line, and we can check based on that whether it is following or not. So maybe I think in the future, the upcoming questions, we can do the realistic check with the given data. So state whether true or false the function norm can be used to check if the distribution is normal. True. Yeah, you can use it to check whether the distribution is normal or not. Moving on to the eighth question. The command AB line is used to add only horizontal or vertical lines in a plot. Add one or more straight lines in a plot with slope and intercept. Draw curved lines in the plot. Okay, so the AB line, it's nothing to do with the curved lines. So option three, we just use regression to do all those things, but we don't use AB line for this purpose. Then either it is first option or second option. So here AB line means A is the um, intercept and B is the slope. Yeah, yeah, I'm correct. A is the intercept and B is the slope. So we can draw one or more straight lines in a plot with any slope and intercept. So that is the answer. And only horizontal line means this is not the correct one. So so okay. We have generated a sample. Okay, much of scribbles that will delete these things. Okay. Here I have generated a sample plot. Um, like using the 50 random variables or now. I'm feeding this x or now 50 random variables with mean phi and standard deviation 2. Then y values with mean 10 and standard deviation 3. Then I'm plotting x with respect to y. Uh, x, y. Plot. Yeah, just a minute. I just lost my internal because of that. Percent switch. Okay. So I think just after this we have lost. We have already discussed like adding one or more straight lines in a plot is the answer for this with the slope and the intercept. If you specify a is equal to some value, it will be taken as slope and sorry, a is taken as intercept and b is taken as slope. So here let's just play around with this. I have fed some 50 random variables to x and 50 random variables to y with mean and given mean and standard deviation, which you can see here. So create a scatter. Oh, I'm just trying to create a scatter plot. Plot x comma y. Main is equal to scatter plot with lines. So that is this. These all points corresponds to the scatter plot. Then yeah. Okay. So okay. So now what I'm trying to do is like from in this scatter plot, I'm trying to draw a red line with slope 1 and intercept 0. You can see AB line slope is 1, which is A is equal to 0, intercept is 0, B is equal to 1, slope is 1 in color red. So you can see this is the one. Then subsequently, what I'm trying to do is like AB line, A is equal to 2, this is intercept is 2, and B is equal to 0.2, so 0.5, which is less than 1, which means it will be dropping 1. So it will be a uh, intercept x intercept 2. So I said, intercept 2, it will be intercepting at some point here, and that is in blue in color. Then I'm drawing a green line with a negative slope that is minus 0.5 in green. So this is just to say that we can add one or more straight lines in a plot with any slope and intercept. For that only, I just wanted to show this example. Okay, ninth question is like the molar heat capacity of copper at different temperatures in Kelvin has been measured and tabulated as follows. Fit this data to a straight line and plot the residues. The slope of the fitted line is okay. So first we invoke this temperature value and specific heat values to variables here temp and Cp. So after invoking, then what we are doing is like we are just yeah. Just one second. Actually, that whatever I have drawn is coming to all the slides, and it is quite disturbing. That's why I just deleted it. So yeah, what was the question? Yeah, we have read the values of temperature and specific heat, and now we are plotting the temperature and Cp values, temperature in X and Cp value in Y, with X labeling as temperature and Y labeling as specific heat, and may title of the plot as temperature versus specific heat. So now we are trying to fit the linear regression model to draw a line. So model linear regression model LM of Cp y with respect to x, Cp with respect to temperature. So now what we are doing is we are AB line model. Model means it will take the coefficient, that is the slope and the linear regression model will have two parameters, which is slope and the intercept. The slope and the intercept will be fed to this fed to the AB line, and then color we are specifying red. So it will draw a fitting line to that linear fitting line, just which follows linear regression. So now the question is not this to draw a slope or anything like that. The question is to find the question is to find the slope of the fitted line. So now we have fitted the line, but we have to find the slope. So it is very easy because we have discussed before also. If you give slope, you can also do like this slope of COEF coefficient, COEF and the coefficient of model. As you know, model is a linear regression model. So it will have slope and intercept within them. So now if you print slope, you will get intercept as 22.887 and slope as 0.005825. So this is the answer for this question. Um, Moving on to the 10th question. In question 9, what can be said about the residuals from the QQ plot? So residuals from the QQ plot can be residuals for the model can be obtained by residuals of model, and we can again we are again actually whatever I've drawn is not going. I don't know whether it's an issue with the. Okay, let's come to this. In question 10, they are asking us to uh, comment anything on the residuals. For that, from the QQ plot. So what we do is that we get the residuals value from the model variable and feed it to a variable called residuals itself. And now we are doing QQ norm of residuals. For that, we will get a scatter on using QQ norm. Then we are drawing a QQ normal line to that, that is QQ line. So if we draw a line, and we can see it is like it's not a completely random one. Rather, it is having a pattern, or in another, it is following a linear fit. It's close to following a linear fit. So that is the answer for that. So residuals are not random. It follows a pattern. So that is the answer to this. I hope you have answered all the questions. You have answered all the questions. So if you have doubt, you can ask.